Okay, let's continue on general chemistry. Now it is going to be the part 31. Now we finished, in the last part 30, we finished the introduction and detailed discussion of basically 8 different kind of chemical reactions. Now the last one is redox. In the syllabus of chemistry 141 was de-emphasized, but I do not think that's the right way to teach chemistry, because redox reaction is so important, and it should be more important than any other type of chemical reactions if you just talk about chemical education. And so I did not go easy and simple. I go detailed, right? Not fully scaled, but quite detailed. Now we finished introduction, classification of chemical reactions, and different feature of different type of chemical reaction. What are the typical products any particular type of reaction will generate or produce? Now we emphasize on these, right? And what is the reaction conditions and their physical states? That's all qualitative analysis, right? Qualitative analysis is important. And before you are able to get into the quantitative, you have to know what compound, what reactants, what products, what compounds are reactants, what compounds are products. Those has to be clear. Otherwise, it's no meaning to do any other quantitative analysis, because the chemical formula, you don't even know that's correct or wrong, right? So now it's up to the point we are ready. We are ready to do what? We are ready to do some quantitative analysis, which we call stoichiometry. Stoichiometry is talk about how much, either by the number of moles or by the mass in grams of all the reactants we have to have in order to produce the amount in number of moles or in quantity as mass in gram or kilogram or tons in the industrial setting, and we are able to get this much of the products. So that is the quantitative analysis we have to get into. Now we are not going to do all these big scale kilogram tons. In the laboratory we're going to do some small experiment, right? Small experiment on the small scale. So we're going to apply everything we learned in the past about qualitative analysis in chemical concept about chemical reactions. Now we're going to apply those chemical with a fixed value of their mass or the number of moles. Now we already finished the conversion between the mass and number of moles for chemical compounds, right? Chemical species. And the bridge in between is what? Is the gram formula weight, or nowadays we call molar mass, right? So it is the conversion factor between the mass in gram to number of moles of the same species, right? So molar mass or gram formula weight, which is the one I prefer, because when we involve ionic compounds, you don't have molecules. So you don't say molecular formula for the ionic compound. You have the single units for ionic compound in the crystalline structure as a single units, like NaCl. That's just one single unit of an endless 3-dimensional array of, right, those cation anion pair alternatively line up in X, Y, Z in 3D space, right? And you cannot get one out or a couple of them out of the crystal structure and single them out as molecules. So we do not call them molecules. Now that's a very important concept, and we're repeating several times already in the past. Now, so we are going to use a small scale. Now this time we're going to start from something soluble, right? Both two reactants were soluble, so in the solution of aqueous solution, and then we are able to make those solution and get a little bit out, and then we make sure there's a certain amount of a chemical compound in each, and then we mix them, right? We mix them, and then to see what happens. Now that is the situation we start. So we start from what? We start from the number of gram in the mass. We not start from number of moles, but we have to go through the mole, the number of moles of each. Then we are able to use the balanced chemical reaction equation, because why? The balanced chemical reaction equation is the key for us to know the mole ratio between reactants and the products. We already done that. That coefficients after the reaction equations are balanced, and then the coefficient in front of each chemical compound formula, 3, 2, 1, whatever it is, an integer number, those are the mole ratio. But mole ratio is the exact integer number, but in reactant we may not run into exactly integer number. Then we're gonna have to learn how to find a new mole ratio. I call it reset mole ratio. We're getting there, all right? But here, let's see. We're gonna pick up two soluble compounds. One is a sodium sulfide. Alright, because the sodium, anything with the sodium is going to be soluble. Remember the solubility rules, right? That one we're going to use to predict the products as well. And then that was lead. Lead is a troublemaker. Most of the time it forms a compound insoluble. But if combined with nitrate, anything combined with nitrate, that compound will be absolutely soluble. So these two compounds, sodium sulfide and lead nitrate, are soluble compounds. So we are able to make solutions. Now, is it clear? And slow down enough, right? So what is the problem here? Simplified as what happens when 100 milliliter of aqueous solution contain 10 grams of sodium sulfide is supporting to 100 milliliter of aqueous solution of 10 grams of lead nitrate. Alright, these two are soluble. But when you mix them, the instant these two start to contact each other, immediately you see some kind of white color powder, or slightly yellow, I think, a powder drop down to the bottom of the beaker, right? That is the precipitation form. So this reaction actually can be written at the beginning. We don't know what the product is. So I would, in your test, in your upcoming final, alright, is going to have this as well. Oh, by the way, I already sent you. I have already sent you about 2-3 weeks ago 2 handouts written by me. One is called Stoichiometry, another one is the art of balancing chemical reaction equation. If you read the second one, you know how to balance a chemical reaction and you know the classification of chemical reactions. Now the stoichiometry, the first handout I'll mention here is talk about exactly this, and I have this exactly set up. There's 3 problems for each, and then each one contains 2 or 3 sub-problems, and you go through step by step, you read them all. That's total 17 page, right? So start it. You study them, and then they already started a couple weeks ago, already gave you the material, right? Since we don't have face-to-face class, right? All right. So this is arrow. It's single one direction. We predict something gonna form insoluble compound as products, right? Now, then when they mix, and then type of reaction, the only thing we are able to figure out is they have two different kind of cation anion, right? That's a polyatomic cluster for nitrate, right? 2 different kind of elements and 4 atoms, right? Each, and O3 is 1 minus charge anion. And you have to have 2 because lead is, right? Lead is the member of a carbon family, but it has 2 common oxidation state. One is +2, one is +4. Now in most of the compound with lead, they were +2. So this is +2. +2 and -2 become neutral. Here, sodium's first alkali metal family is +1. Sulfur can have what? Sulfur can have +6 or -2. So in this case, right, the compound, you remember the trend periodicity, right, of the oxidation states on the periodic table I introduced very, very early. It's been month, right? And the sulfur is 6A major group, which is oxygen family, right? Oxygen family. They have a very common oxidation state was plus 6A6, right? And then the -2. So these two, the absolute value add up is going to be 8, right? That's very coincident. All right, very, very funny. All right, so it's very, very unique, right? Let's put it this way. So this one is +1, right? The +1. This one is -2, and 2 of them, and this one is +2. All right, this whole thing is not inside is a +5, and then -2 outside, and then entirely outside is going to be 1 minus as this nitrate NR. Now the only thing that can happen is they exchange their partner. We call double replacement or double displacement. So let's say this is going to be double displacement. So the sulfide, right, exchange with the position of what? Nitrate, right? They exchange, and put the arrow down there, right? Exchange, right? So that is the double displacement, right? Double displacement reaction. So that's a type of reaction we decide, right? Double displacement. So after you exchange the anionic partner and they form new compound, that's the only thing we are able to. So type is double displacement, right? That's display double displacement reaction, all right? Now then we are able to do what? We predict the products. By what? By solubility rule. Right? The solubility rule tells us the compound after exchange partner will be what? Will be the first one would be what? Would it be sodium nitrate? Now, do we have 2 this time? We don't have 2 because sodium +1, nitrate is -1. They are perfectly matching each other, right? And we know sodium for alkali metal, they are soluble with anybody else, and furthermore, the nitrate with anybody else also soluble. So these two. Anything with these two, even they pair them up, is going to be completely 100% soluble, strong electrolytes. So the physical state is going to be what? AQ. Now, in my test, I am not going to just put this one. I will give you more hint for you not to miss any points, because every blank you're going to fill up correctly, get 1 point for the written part for this stoichiometry in your upcoming final. Now, I am not going to give you just like this. I will give you some hint. Right here, the line blank means you're going to put chemical formula down there. And then I will leave a parenthesis blank for you to fill up correctly the physical states by understanding or using solubility rule table. I will give you solubility rule table. It's an open test, right? You should use that. I'll just remind you. And then you have, after you exchange partner, you have another product, right? It's going to be the compound formula as well as the physical state. Now, I forgot this. Actually, it should be this. You will see this. You have another parenthesis in front, right? Another parenthesis in front is going to be the coefficient when you balance chemical reaction equations, right? And then the formula, and then the physical state, and then you have coefficient and the compound formula and the physical state, or like that, right? So every one you feel correctly, don't miss any one of them. You can say this one, just put one down there. Or you just, if you have 2, then you put 2, right? Now this one is aqueous, but then here, now we haven't gone to balancing here, right? The aqueous, but then the second one is going to be what? The lead combined with what? Lead combined with sulfide. Lead is +2, right? +2. Sulfide is -2. So they perfectly matching, right? But what is the physical state? Now check the solubility rule says sulfide, right? Sulfide is soluble. Remember A and B, right? Sulfide was the last one, or in the middle, and but it does not, right? It does not dissolve or it's not soluble when it forms with lead and the mercury and other cations. So this time the PBS, PBS is S. S is what? S is stands for solid, right? So this one will drop as precipitate. So it will precipitate. So it's PPT right here. Right? Now after you did that, we are able to completely have a chemical reaction equation, right? So number 4, right? So you're going to balance the chemical reaction, right? Balance the chemical reaction. Now, in this case, let's check the metal, because we do have metal, but 2 different metals. One is the sodium, right? Alkali metal. One is the lead, right? It's a toxic metal. We all know lead is toxic, right? That's why people avoid using leaded gasoline now. It used to be lead. So what happened? Sodium, you got 2 right here, subscript 2, because sulfide is -2. Right, and then so you have a 2 here, and only 1 here. So this will be what? You have double this, right? Become. But when you double this, you double the nitrate as well. Well, fortunately, we already have a double nitrate here in the lead nitrate. There are 2. So nitrate, by the way, it's also balanced, right, during the process. Then check the lead. Lead is got 1, right? On the other side is 1, so it seems it's okay, right? And then the sulfur. The sulfur is 1 right here, so it is balanced. So it is balanced. The chemical reaction is going to be what? The chemical reaction balanced is going to be Na2SAQ. Let's rewrite it, right? And P. Now that's 2 right here, right? And lead nitrate. Alright, it is aqueous as well. But then you have, right? Oh, that's not 2 right here. 2 is not here. This 2 is going to be the second one. Make a mistake along the way all the time. Prepare this kind of a lecture online. Try not to make any mistake. And here is going to be exactly the same as PBS. Now PBS what? PBS is the public broadcasting system, right? PBS is a channel, right? Channel. So that is the products. Now it is. Now then the next steps. Since we have a balance the chemical reaction with coefficient as a 1, 1. We don't write a 1 because we omit it, simplify, and then 2, 1, right? So we're going to indicate the mole ratio. Mole ratio means what? Between, right? Between all products and the reactants. And products, right? So what is the mole ratio? This is a 1. This is 1 to 2 to 1, right? 2 to 1, right? All right. So at this moment on my handout, I put one paragraph down there as a statement. If you read it, it says the story. What the balanced chemical reaction tells us. What story the balanced reaction equation tells us, right? So we're gonna put this number 6, the story. A balanced. The story, balanced. Equation. Right. Right. So what we're going to put down there. The story is this: if we have a 1 mole, all right, of sodium sulfide, it can react completely with 1 mole of lead nitrate in order to produce exactly 2 mole of what? Sodium nitrate and 1 mole of lead sulfide solid. Right, that's the story. So if we put it down here, so what is it? Okay, here's a 1 mole of, right, is able to completely react with 1 mole of lead nitrate, right, to produce exactly what? 2 moles of sodium nitrate and 1 mole of, now let's put here solid, as physical state indicated clearly, emphasized clearly, 1 mole of solid what? Solid lead sulfide. Alright, that is the statement. Based on what? The mole ratio. Right, what is this whole thing is talk about? The mole central theme. The mole central theme of what? Of chemistry, right? Of chemistry, of quantitative chemistry, quantitative analysis. Now, so by this story we understood, simple, right? Based on the coefficient of the balanced chemical reaction equation, such 1, 1, 2, 1, right? 1 to 1 to 2 to 1. That's the mole ratio. But do we have exactly 1, 1, 2, 1? Oh, we don't know 2, 1, but we have exactly 1 to 1 ratio for number of moles between 2 reactants? Not necessarily. If we do, that's okay. So what is it going to be? If we have 1 mole, what is the molar mass for this? Sodium 23 times 2 is 46. 46 plus 32, right? Sulfur 32. 46, 32 is 78. Right? So this 78. If we have 78 grams of this, right, into a solution, and we have this, how many grams? Let's see, lead is 207.2, so that's 414. 414, oh, that's just one, 207. This is 62. Naturally 62. 62 times 2 is 124. 124 plus 207, right? Is it 124? Yeah, 124 plus 207, 324, 331. 331. So if we have 331 grams of lead nitrate, and then we mix these two solutions, right? And then it will exactly produce 2 mole of sodium nitrate and 1 mole of PBS, right? But how many grams we have? Do we have 331 of lead nitrate? No, we only have 10 grams, right? So little, right? Experiment in lab, right? So this 10 grams is not even, what is that, 78? This is 78, right? This is not, this is only about 12%, right? 12%. So that is not going to be 1-to-1 ratio, but we need to find a 1-to-1 ratio in this case. So what happens? All right, what happens? What happens is we have to find how many moles out of 10 grams of this and 10 grams of that, right? And then we are able to deal with how many we are able to exactly form. So let's find it. So the number 7 is a given quantity. Given in gram, right? Now what is that? This one is 10 gram, right? That's 10 gram. And this one is 10 gram. Both 10 gram, right? And then in order to find the number of moles, right? Remember we did it very early when we introduced the scientific base units, right? Mole is number 5th. The 5th units we call the amount of quantity of a matter, right? So the quantity of matter, right? And then, but then I did not stop there. After I introduced the mole, long time ago, now you are already, you should already familiar with that. We continue on the molar mass, right? The gram formula weight, and the Avogadro constant. How many particles would be considered as 1 mole, and depends on the nature of the particles, what elements, and go by the periodic table of elements, find their atomic mass, and we introduce the graphite experiment. How could any unit conversion between 2 different units and then has a 1-to-1 ratio, right? Because the we can directly use the atomic mass unit value for any elements and change the AMU into G as gram, then we find the molar mass, right, for the elements. But that is already introduced. Then we know how to convert gram to moles, number of moles, by what? Gram is smaller units, mole is bigger units, because 1 mole is always more than 1 gram, right, for anything, right? So for even hydrogen gas, is 1 mole is 1, hydrogen gas is 1 times 2 is 2.016 gram per mole of hydrogen gas. So we use the tips I introduced in my class for quick and correct unit conversion, right? We convert small unit gram to number of moles, we divide the conversion factor, right? Now, so here we need to know the gram formula weight of the reactants, right? Gram formula weight. The first one we already talked about, roughly 23 times 2 is 46, 46 plus 32 is in the 78. So this is going to be 78 gram per mole, am I right? Now that one is 331 gram per mole. We already estimated, right? Then in order to find the number of moles, we divide these gram formula weight of the compound into the mass in gram they have, or the given, right? So we divide with a simple right here. And that's where I listed this whole in this kind of order. So we do this. Alright, is that division? Yes, division. When we divide, then what happens? This one, right, the mole goes on top, and the gram cancel gram, you got moles instead of gram disappearing, right? So the mole goes up, right? It's called reciprocate, right? Reciprocate time. And then this gram cancel gram, so you got moles. So what is the formula of this? And then in the next step, there's a number of moles for the reactants, right? So we need a calculator, right? We need a calculator. Time's almost up, but that's okay. And we continue the next section. So what it's going to be is going to be the 10 divided by 78 roughly. I did not use decimals. 0.128. So this is going to be, so 0.128. That is not the marker. Mole, right? Now that's first one, right? So Then time's up. We continue the next session. All right, continue from here. We left off. All right.